Hello, everyone. Good morning. My name is Sanjeev, and I'm here to give a brief introduction about decision trees. This will be a very short video due to time limitations, but however, I'll try to explain it as simple as possible. Before we proceed, I would assume that we already have a basic understanding about what are supervised learning and I mean, what is supervised learning and what is unsupervised learning, and we also know some concepts about coefficients and correlation. What is a predictor variable and what is a independent variable? What is a target variable and all. And we also know some basic understanding about what we are trying to predict, what is the business problem and all. So let us go deep about decision trees. So basically, this is a concept where we try to use for or for a data set where we know what is the ground truth. For example, if we are working for a bank and we try to understand if a given loan application is eligible to be given loan or not. So that happens based on many decisions. For example, if a client is walking into the bank and he or she is looking for a loan of 2 lakhs, for example, but their salary is not about 10,000. So based on one criteria, based on some questions, we decide if that person who is walking into the bank is eligible for a given loan or not. So whenever we have a data set like this, where we can derive the final answer based on numerous questions. The questions could be as simple as three or four, or it could be more than three or four, based on how many complicated questions that we have and how many complicated recordings that we do for a given person or record. So for these type of data sets, I think decision trees can work very well. Okay, so whenever we have such kind of data sets where we can draw the decisions based on simple questions, simple flowcharts, we can use decision trees, and we can keep on asking these questions until we reach our final answer. So I'll give you a brief on this kind of data set. I'll show you how this decision tree works. So suppose we have a simple loan bucket like this. I'm sorry, I have a dual screen. I will be looking at screen two. So I'm not looking at the camera all the time when I'm explaining. So we have a decision tree. We have a simple loan bucket. We are trying to identify if a given person is working as a in a private sector or in a government sector. And if you can notice, what we have is like if the person is working in a private sector, we have a threshold of 50,000 salary, and if the person is working in the government sector, we have a threshold of 30,000 salary. So again, if the in the private sector, if the person is higher than 50,000, we check the next level. How many years he has been working in the same company. The same is the case with government sector. We are checking if how many years he is working in the government sector. So that is how we tend to answer. If the person is not getting 50,000 salary, we say he is not qualified for the loan. Similarly, if the person is not qualified, not having a salary of 30,000, he is not getting a loan in government sector. And so on, we continue to ask these questions. We look at how many expenditures he's having in the current setup. So for example, if we say the salary of the person is say 40,000. Okay, in this 40,000 he already has a commitment of 20,000. So because he has already achieved the 50% threshold, we cannot give loan to this person. So that is how we tend to ask more and more questions, and we try to derive if the person is going to achieve a loan or not achieve a loan. Okay, uh, so we can keep adding more questions to it. We can complicate the data, and we can increase this tree. Like the tree keeps on increasing based on how many rules or how many sets of questions that we are trying to ask. The key thing is how to derive this, like how many set of questions. This is called as a node. This is called as a child node. And for this child node, these are the leaves, child and leaf. So how many child nodes to make and how many leaf nodes to make, that is the concept behind decision tree. And how to achieve this is what we are going to look at today. So all this happens based on something called as entropy and information gain. So I'll try to explain that in the next slide. So I hope this is clear to you that we have a loan data set and we're trying to understand whether a person is eligible to take a loan from the bank or not. So all this is happening based on multiple questions, and we are achieving this by forming some kind of a flow chart. Now, what you see on screen is some kind of a flow chart where we are asking question, and based on the question, if it is yes, we are taking some decision. If it is no, we are taking some other decision. So every time you go to a no step, we say that the person is not qualified. And every time you go to a yes step, we are trying to ask another question and try to see if still there is a concept of like if still there is a possibility of giving loan or not giving loan, right? Now, uh, what we basically would be doing is we are trying to understand how many splits that we have to make. So as I said, like splits are basically child nodes or leaf nodes. This split is based on something called as entropy. Now I use two parameters, like two keywords that one is entropy and another one is information gain. So first I'll discuss about entropy. So what happens is, suppose we have a discussion called child loan, like a student loan, not child loan, student loan. So basically, bank says that a person who is below 35 years is eligible for student loan. So now our data set has some age distribution like this. So a person like we have 18, we have 20, we have 45, we have 30, and we have 50. Suppose there are five records, and for all these five records, as per the bank criteria, this person with 18 years is eligible for loan, 20 years is eligible for loan, 45 years is not eligible for loan, 30 years is eligible for loan, 50 years is not eligible for loan. Okay, every record has an outcome. As I said, like this is a supervised learning. We already know what the ground truth is. The ground truth is every record which is above 30 years is not eligible for loan, and every record which is below 30 years is eligible for loan. Okay, so for in this case there are two outcomes, eligible and not eligible. So if I divide this data set into two parts, one lesser than equal to 30 and one greater than 30, then what I'll have 18, I'll have 20, I'll have 30 here, and I will have 45 and 50 here. So this particular child node belongs to one class where the these records are eligible for loan, and these particular records where the age is greater than 30 are not eligible for loan. I have two classes, 1 and 0. Now if I make the odds out, so in this particular class all of them belong to 1, right? So I want to understand what is the uncertainty. Now, if I go for uncertainty, I can calculate the uncertainty by using this formula. Odds into log of odds, I can keep on summing. Now, in this case, all of them belong to one class. So what happens to log 1? Because all of them belong to one class, I'll say log of 1. Now, log of 1 is 0. So the entropy will become 0 for this class. 0 into anything is 0. In the case of this one, log of 0 is infinity. Okay, 0 into anything is again 0. Now what happens, this is completely belonging to one class. All these records are one class, and all these records are one class. Now entropy is 0. When entropy is 0, the information gain is very high. So we can say that they are inversely proportional. Lower the entropy, higher the information gain. So we have to divide the data set in such a way that we try to make this partition as the information gain as high as possible. So when you may achieve this, there is a possibility that the certainty is measured, and based on the certainty we are trying to divide the records into set of child nodes. So in this case I divided the set into ones and zeros. In the real example, in the real world scenario, the case may not be as easy as possible, as easy as this. So for example, what happens is, the for a given data set, as I said, like we have 18, we have 20, and we have 30. But for some other reason, age is not only the criteria. There could be some other question like financial constraints. So for example, I have a record of 18 and 20 are eligible for loan, but for record 30, the loan is not eligible. So in this case, what has happened? The sparsity has increased. There is an uncertainty, because our question was higher than 30 should not be eligible, lesser than equal to 30 should be eligible. But in this case, lesser than 30, this is not eligible. So what has happened? The uncertainty has increased. So in this case, what we'll be doing is, so we'll be looking at log of odds. So 2 by 3. I have two records which says loan are eligible, and one record which says loan is not eligible. So in this case, again, we can use the same formula. We can use 2 by 3 into log of 2 by 3 plus 1 by 3 into log of 1 by 3. So we'll add a negative symbol just to make it the reverse way. As I said, like lower the entropy, higher the information gain. So we will be using this formula to calculate entropy. We don't have to do it anything, like, you don't have to run into calculating entropy and all. When we use Python and when we try to apply the model, decision tree will inbuilt use this formula to do the splits. All we have to do is how many splits that we have to make and how many child nodes that we have to make. So even that is parameter. We can use all them in all of these things as parameters and pass it to the model, and model will be automatically built. So we don't have to worry about how to use this formula, how to calculate all this out. This is only for understanding purpose, that we are trying to see how the split is happening in the backend. All right. I hope this is clear for you, how the entropy and information gain is made. So we try to do this split uh, until we reach a position that there are no further splits. For example, in the previous case where less than 30, all of them belong to class 1, and greater than 30, all of them belong to class 0. We cannot ask further questions because that is the end of it. All of them we have classified as ones and zeros. Let us assume that there are, even after asking this question, there are a couple of cases where some records are 1 and some records are 0. For example, like less than 30, some records are 1, some records are 0. So again, we have to ask further questions, so that we have to split ones and zeros. That is how you continuously keep asking these questions until we reach to a point where we cannot ask further questions. That is a point where the growth of the tree stops. Okay, that is how the decision tree works. Now, what happens is, I'll tell you what we usually end up with when we are using decision trees. So the problem with decision tree is it continuously keeps on growing until it reaches the final question. So what happens is, when you have a trained data set, it will perform very well on the trained data set. I'm talking about decision trees. And the problem with decision trees is, when we train a data set on subset of data, and it will perform very well on the subset of data. But what happens is, when it comes to unseen data, that is where we try to end up with getting a problem of a lower accuracy, because the decision tree could not split on the unseen data. It cannot perform very well on the unseen data set. So what happens is, we should not be allowing the decision tree to grow continuously. So there should be a stop. For example, we can say the depth of the tree should be not greater than 3. So what I'm doing is, I'm growing a tree. I'm growing a tree like this, but I'm saying beyond this point, don't grow. So for example, if we are dealing with a loan bucket again, we have male and female data set. So few records are male, few records are female. So is it viable to ask If the person is male, give the loan. If the person is female, don't give the loan. We cannot do that, right? So there is no point in asking segregating the data set of males and females. So you can consolidate these data set into one. We can make all these this question as, irrespective of whatever the answer is, put them into one category, something like this. So based on the questions, we can say once we reach this threshold, stop asking further questions. So I don't want the decision tree to ask whether the record is belonging to a male or whether the record is belonging to a female category. So that is how we can prune the tree. We can stop the tree from growing and limit the tree from asking further questions. That is how we can achieve the success. We can achieve a trade-off between accuracy and accuracy between the positive outcomes and the negative outcomes.